Hello students, we have learned about the types of friction in which we have seen the static friction, limiting friction, kinetic friction or dynamic friction. Kinetic friction or dynamic friction further classified in two categories. The first one is the sliding friction and second is the rolling friction. We'll define sliding friction as the opposing force that comes into play when one body is actually sliding over the surface of the other body. And for example, when a flat block is moved over the flat surface of a table, the opposing force is sliding friction. Rolling friction will define as the opposing force that comes into play when one body is actually rolling over the surfaces of other body. For example, when a wheel, a circular disc or a ring or a sphere or a cylinder rolls over a surface, the force that opposes it is the rolling friction. Further, we'll see laws of kinetic friction. There are three laws of kinetic friction. The first one is the force of kinetic friction, that is Fk, we have seen in the graph previously, is directly proportional to the normal reaction R between the two surfaces in contact. That is Fk is equal to or Fk is directly proportional to R. We'll write in this way. This is, we can see here, we'll see the Fk is equal to or directly proportional to R. Or we can say Fk is equal to a constant will apply here, that is mu k R. Okay, this mu k is called the coefficient of kinetic friction. And we'll see the third point here. The third point say that it is, the third point is force of kinetic friction is independent of speed of sliding, rolling, if the heat produced does not change the condition of surfaces in contact. Okay, so these are the three laws of kinetic friction. Now we'll see the cause of rolling friction. The cause of rolling friction is when a body rolls on a level track. The area of contact is very small. Therefore, pressure exerted, which is equal to weight area, is very large. This causes a depression in surface below and a mount or bump in front as shown in figure. You can see the figure adjoining it. Okay. So, in turn, the surfaces of rolling body in contact gets slightly compressed. Thus, a rolling wheel constantly pulls out of depression and goes uphill on a mount. It is represented here, the mount is represented as Lm. Simultaneously detached itself from rod Kl, which is opposed by the force of adhesion between the surfaces in contact. This causes rolling friction. When a tire is properly inflated, it becomes hard and gets compressed by the rod to a much smaller extent. Due to it, the opposite to the motion due to adhesive forces become less. Therefore, rolling friction reduces. Hence, it is easier to drive a vehicle when its tire are fully, means when its tire are fully inflated. Okay, so note that the velocity of point of contact of wheel with respect to the floor remains zero all the time. All the center of the wheel moves forward. Therefore, rolling friction is often quite small compared to the sliding friction. That is why heavy loads are transported by placing them on cart with wheels. The sliding friction is converted into rolling friction, and for example, rolling friction of a steel on a steel is hardly 1% of a sliding friction of a steel or on a steel. Okay, so static friction is we'll see now the static friction is the self adjusting force. We'll see this means that neither the magnitude nor the direction of force of a static friction is fixed. Both these things adjust themselves according to the applied force. Already I have explained to you about the static friction. Static friction is that opposing force which comes into play when the object is not moving at all or the motion is impending. Okay, the impending motion is there. So that means whatever force are applied here, so the static friction also will adjust itself, and you will see here we have seen that unless the block starts moving, F equal to P. F equal to P. P is the small force, small applied force. Okay. So that is the force of a static friction is always equal to the applied force, and when we decrease the applied force, the force of a static friction also decreases accordingly. Further, the direction of the force of a static friction is always opposite to the direction of the applied force. For example, when we try to move the body to the east, force of a static friction is to the west, and we try to move the body to the north, force of a static friction is to south, and so on. Okay, now we'll see here, that means the static friction adjusts itself so that its magnitude is equal to the magnitude of the applied force and its direction is opposite to that of the applied force. Hence, static friction is a self-adjusting force. And one more thing you have to keep in your memory, remember that the friction arises only when body is actually sliding, rolling over the surfaces of another body, or the body is simply trying to roll over the surface of other. Further, static friction alone is a self-adjusting force matching the growing applied force. Limiting friction, dynamic friction are not self-adjusting. Their values are fixed. Be careful, limiting friction and dynamic friction are not self-adjusting. Their values are fixed. Okay, now we'll see the laws of limiting friction. We will see the 4 laws of limiting friction. The first one is the magnitude of the force of limiting friction, F, between the surface of two bodies in contact is directly proportional to the normal reaction R between them. That is, F is directly proportional to R. When a body is heavy, normal reaction, that is equal to, means the normal reaction we are representing with letter R, sometime representing with letter N, capital N, and that is equal to mg. This increases, therefore F increases, hence P is equal to F increases, and that is more force is required to move a heavier body than to move a lighter body. I will just explain you in this manner here. You will see now. Just now we are talking here, this we have seen the Fk is directly proportional to R. So you will find the limiting friction. We are talking about the limiting friction representing with letter L. So Fl is directly proportional to R, that we can say. Okay, and this is what here, but we know that R is directly proportional to mg, or R is equal to mg simply. Okay, so in place of Fl is directly proportional to R, in place of this R, if we'll just write mg, so here it will become Fl directly proportional to mg. That means more the heavy weight is there, or the object is heavy, so the friction force is more. Okay, so more limiting friction force should be appear or should arise between the surfaces in contact. Okay, so this is the first law of limiting friction. Okay, now we'll see here the next law, that is the direction of the force of limiting friction is always opposite to the direction in which one body is at the verge of moving over the other. The force of limiting friction is always act tangentially along the surface of contact of two bodies. The force of limiting friction is independent of the apparent area of contact, and so long as the normal reaction between the two surfaces in contact remain the same. The force of limiting friction, this is the fourth law, the force of limiting friction between any two surfaces in contact depends on the nature of the material of the surfaces in contact, that is force of adhesion and their state of polish. Okay, now we'll see after this the experimental verification of the laws of limiting friction. Just now we have learned the four laws of limiting friction, and we'll see one by one the verification of these laws. So to verify the laws of limiting friction, we take two exactly identical rectangular blocks of wood A and B. You can see the figure, it is represented here in the figure 5.24. You will observe it carefully. Okay, so you will see we have taken the two blocks exactly, means identical, that is A and B, each of same weight mg. Each block is provided with a hook on one side. The block is placed on a horizontal table provided with a frictionless pulley on one side, and one end of the string is attached to the hook of the block. The string is then passed over the pulley and a pan is attached to the free end of the string. Any number of weight can be added to the pan. We adjust the weight in the pan till the block just begins to move. The applied force P at this stage, that is equal to weight of the pan plus weight in the pan, gives us a measure of force of limiting friction F, and so that we can say F is equal to P. Once again I am telling to you, P is the applied force, and already we have seen the R is equal to mg. R is balanced by mg, or you can say simply mg is balanced by R. Okay, now the first law, which state that the magnitude of the force of limiting friction, that is F, is directly proportional to R. So we are verifying this. So for that you will proceed as explained above and determine the force of limiting friction in case of block A. You will find, now place the block B on the block A. The weight is double, therefore the normal reaction also become double. Repeat the experiment and find the force of limiting friction in each case. In this case, it is found to be 2 times the force of limiting friction in case of block A. Thus, we find that when R is doubled, F is also doubled. Hence, it is proven F is directly proportional to R, which is the first law of limiting friction. Now, you will see the second law of limiting friction. It is said that the direction of force of limiting friction is always opposite to the direction in which one body is at the verge of moving over the other. Okay, so we are proving this statement now. As is clear from the above discussion, in equilibrium R is equal to mg and F is equal to P, that is force of limiting friction is equal and opposite to the applied force P. Hence, the direction of the force of limiting friction is always opposite to the intended direction of motion of the block. This verifies second law. In the arrangement, you will see shown in the figure, the second figure you will observe here, that is the figure 5.25 given here. Figure 5.24. If pulley were on the left, weights have to be put in the pan to move the block to the left. This means force of limiting friction in that case would be to the right. This confirms second law. Okay. Third law. Third law, the statement was the force of limiting friction is independent of the apparent area of contact. Okay. So we will verify this law also, the third one. So for that we'll see now. Join the two blocks A and B and place them on the table as shown in figure 5.26. Repeat the experiment and determine the force of limiting friction in this case. It is found to be same as in case when block B is placed over the block A. The total normal reaction in the two cases is the same, but the area of apparent contact in case shown in figure 5.26, the previous figure, and the is double, since F in both cases is the same. You will find, I am just showing you the previous one, you will see in this figure. You will see the second figure in which the block is one above over. Okay, one means it is placed like the area of contact is same. If you just place the block A, then also the area of contact is same, and if you place the block B over A, then also you will find the area of contact here same. Okay, but when you just do the arrangement like this figure, you will find the area of contact will be increases. So but you will, what you will find here, the force of friction is calculated here is same. That means it proves here the area of contact will not affect the force of friction, and that is the third law of this is the third law of limiting friction. Okay, so what you will find here, since F in both the cases, the previous case when blocks are kept one over another, and here the blocks are kept in the like the bogies of the train like a structure, then also you will find the same type of limiting friction will be there. So it proved that the limiting friction does not depend on the apparent area of contact between the bodies, so long as normal reaction between them remain the same. This verifies third law. Now fourth law we will see. Take the rectangular block A, make one surface of A smooth and well polished and the opposing surface of A very rough. Repeat the above experiment and determine the force of limiting friction. First, when rough surface is in contact with the table and when smooth surface in contact with the table, we observe that the force of limiting friction is less when a smooth surface is in contact with the table and move when the more when the smooth surface is in contact with the table, and you will find that it is more when the rough surface is in contact with the table. Hence the force of limiting friction depends on nature of surfaces in contact, and this verifies fourth law. Similarly, if we take two blocks, one of wood and other of metal of same weight, F is either case is different. This also proves that force of limiting friction depends on the nature of material of the surface in contact. Nature of material of surface in the contact, if we are saying, that is just come to the modern view of the modern view or modern cause of the friction. It predict or it verified that that is the force of cohesion and force of adhesion. If we are talking about the nature of material of the surface, that means if the different material you will take, the different force of adhesion will be there between the two surfaces which are in contact. Okay, so this way you will we have proven all four laws of the friction, limiting friction. Okay. So next we'll see coefficient of friction. In coefficient of friction, you will find, according to the first law of limiting friction, F is directly proportional to R and F is equal to mu R. So mu, which is called the coefficient of friction, is equal to F upon R. So now we are in the position to define here to define the coefficient of limiting friction, and it is the coefficient of limiting friction between any two surfaces in contact is defined as the ratio of the force of limiting friction and normal reaction between them. The value of mu depends on nature of the surfaces in contact, whether dry or wet, rough or smooth, polished or non-polished. Second, material of the surfaces in contact. Third, temperature of surfaces in contact. For example, when two polished metal surfaces are in contact, mu equal to 0.2. When these surfaces are lubricated, mu is equal to 0.1. Between two smooth wooden surfaces, mu varies between 0.2 and 0.5. Obviously, mu has no units. Because this is the ratio of the same type of physical quantity which are having the same dimension. Okay, so when a body is actually moving over the surface of another body, we replace F by Fk, the kinetic friction, and mu by mu k. So now the equation will become what? The equation will become mu k is equal to Fk upon R, where mu k is the coefficient of kinetic friction, Fk is the kinetic friction, and upon R is the normal reaction here. So mu k is then called the coefficient of kinetic or the dynamic friction, as Fk is less than F. Therefore, mu k is always less than mu. That is, coefficient of kinetic or dynamic friction is always less than the coefficient of limiting friction.